to prove the convergence of a p-series. This is number, we made it up. So what? We have the sum from 1 to everything of 1 over x to the p, and whoa there. Carbon needs to match the break. That should have been an n. Now, to use the integral test, we must first show that it's continuous. And if I was going to draw that guy, when p is odd, or at least not even, it looks like that. But we're worried about continuous on the domain 1 to infinity, and it is. But what if p was even? Then it would look like that. Still, continuous on the domain we care about. What else do we need? We need to see it as a positive. Oh, look, check, check. Both of them above the line. Now what? We need to show that it's decreasing. And how? We look at the next term, an plus 1, and we wonder, oh, which one's bigger? Is this one bigger? Or is it this one? Well, I like big denominators and I don't know why. It's the Sir Mix-a-Lot postulate. It makes the fraction smaller. So yes, it is decreasing. The next term is smaller than the term that you're at. Now we can proceed with the integral test. So I'm looking at an integral. I'm going to leave that little dot down there because I know it's going to bother somebody. No, I'll go ahead and I'll get rid of that. So then what? We're looking at the integral from 1 to infinity of 1 over x to the p dx. It's improper, so we change the limit of integration to a variable that we like. Looks like we chose h. So it's the limit as h goes to infinity of 1 to h of 1 over x to the p dx. Now I'm going to rewrite that integrand, man, just so that I can make it clear that we're using the power rule. So we integrate that. How? We add 1 and we divide by it. Notice that p is just a constant. It's some number. So we add 1 and we divide by it. And then the limit, we're going to evaluate it using the fundamental theorem of calculus, which is why we needed to change it to a limit notation so that we can use the fundamental theorem of calculus, because that only works on closed intervals. So then, yeah, it's upper minus lower. What's upper? Now, that part here is what we're concerned with, because it's the only part with h. So then we run that limit, and it's only going to converge if our infinity is in the denominator. And our infinity is in the denominator of minus p plus 1 is smaller than 0. So we go and we find out what our p is. Our p must be bigger than 1. So by the integral test, if that interval converges, then the series converges. Can p be 1? No, p can't be 1, because look at that denominator. Then that limit wouldn't exist. And if that limit doesn't exist, then that integral doesn't converge. If that integral doesn't converge, then the series diverge. And then we restate. That converges when p is bigger than 1.